it doesn't work out, you learn. If it works out, then, it's still a learning process. So you keep on practicing. And also a reminder for the Python part, you also need to practice. If you need to really learn a good programming language effectively, you need to practice, because it's like math. You'll forget if you don't practice. If you don't practice, you'll just wake up and you don't even know how to define a variable because you've not practiced. So you keep on practicing, even in daily 10 minutes. Just look at something regarding Python. Yeah, so today we have a lot to cover, and if there's no comment or question, allow me to start. Okay. Also, another. Sorry, yes, say something.
I wanted to ask, where can we get notes on the Python libraries?
Okay, so for the resources that I gave the W3 schools, they have sessions for pandas, NumPy, Matplotlib. So you can go through the W3 schools website. That will assist you. And also, I sent a slide share on the libraries. But if you feel those resources are not enough, I'll add more resources in the due time, maybe tomorrow or before our next class. Is that okay?
Yes, thank you.
Okay. I'm hoping everyone can see my screen. I'm going to give a high level explanation because this part is supposed to be from our previous class. We have a lot to cover going forward, but I also don't want to skip the basics, because if I skip the basics, I'll just be doing nothing with you guys. So it's important that we all grasp the basics. So we did Python general as a programming language. So Python is wide. It can be used in data, in web, to make APIs, etc. And I also said it's an open source language, which means people keep on it's out there for everyone, which means it has a great community and people keep on improving and refining, especially with the libraries. So we have libraries that we're going to use mostly for data manipulation, that is like data analysis. uh, before you give model a data, you have to clean your data, because we believe that garbage in, garbage out with computers. So if you give your model messy data, dirty data, you're going to get an output which is, dirty. So it's a necessary step. Even if you're doing, I don't know, whatever you're doing, whatever you're giving AI, even for the chat GPTs, the large language models, they have been given clean, good data. And Python is very important in cleaning data, and there are libraries that do that work. So the good thing about Python, we have libraries that you don't need to code everything from scratch. You can just use libraries to do tasks. Okay, so I'm just going to give a high level explanation of the following libraries. So the most popular one, this one is NumPy. It's used for, let's say, mathematical operations. For example, it has inbuilt features for mean, median. If you're doing anything mathematical, you're going to use NumPy. And when you're using NumPy in Python, okay, before you use NumPy, let's say you just installed your environment, there's a method of installing these libraries, which is called pip install. Allow me to just write. Let me just create a small section here for the explanation. Or let me just add a small slide. Next slide. So basically, if you've installed, okay, if you're using Google Colab, you don't have to pip install, but sometimes you usually have to if the library is not there. So this is like the command for installing Python libraries. So depending on what you're installing, so you can install NumPy, Pandas, Matplotlib, etc. Depending on what you're installing. And also when you want to use the library, you just say import. So just import, it's supposed to be small letters. Let's say NumPy, Pandas, etc. So you can import NumPy as NP, which means you've already given it an alias term. So when you're using NumPy, you just say np.min. But if you don't give it an alias, okay, the alias is np, there's no another alias term for NumPy. If you don't give it, you're going to use it as is full. Okay. So basically, NumPy is for, I'll just say mathematical operations, and it's also important. So you find yourself installing it almost every time you're about to do exploratory data analysis. And if I say exploratory data analysis, you're going to cover that. So don't worry. The other library is Pandas. NumPy and Pandas are usually, closely related. Pandas is for data manipulation. So if you want to do the EDA or the data analysis using Python, you're going to do most of the things with Pandas. So Pandas has some features such as data frame. So if you did the assignment, you made a data frame from the data that we had scraped from our website. So the data form for Pandas is called data frame, but it has a lot of operations, mostly involving data. If you give it like data in Excel, you can view the columns, you can view the column data types. So most of the time, you will find yourself doing the data manipulation using Pandas. The other one, let me just cover the ones for EDA first. It's called Matplotlib. So Matplotlib, it's for plotting. Let's say you want to plot a graph from your data, you're going to use Matplotlib. And it's the same thing. Import Matplotlib as, I think it's SMGP. Yeah. And Seaborn, it's like subsection of Matplotlib. So you'll find yourself sometime using Seaborn to create your visuals or Matplotlib. So basically, they are used interchangeably. If you do your research, you'll find like maybe Seaborn gives more dynamic feel of the visuals than Matplotlib, but sometimes it's not that different. But it depends. So those are like the major libraries that you're going to use for EDA, exploratory data analysis. So the other one is scikit-learn. Scikit-learn library is for machine learning now. So in today's lesson, we're going to see more about like machine learning, what makes it, how do we make a machine learn? What are some of the things that we need to do to a machine so that it learns? So scikit-learn is where the algorithms for machine learning are. So if you want to use an algorithm, for instance, linear regression, I'm just going to give those examples because I know by the end of the class, you'll have understood what linear regression is. So you're going to use scikit-learn. It has all the machine learning algorithms. And the other library, it's SciPy. SciPy is basically built on NumPy. So it's like the scientific aspect of it's like a science library for data analysis. Not exactly data analysis, but it's more of the scientific functions. If you want to access the scientific side of coding, you're going to use SciPy. Yeah. The other thing that you're going to cover in Python, the frameworks for deep learning. The first one is called PyTorch. That one you're going to cover later on when you start doing deep learning. when we understand what deep learning is and why we are learning about deep learning. So these are not like, okay, they are frameworks. And deep learning, we have PyTorch and TensorFlow. So in TensorFlow, you're also going to learn another section of TensorFlow that is called Keras. So don't worry about the names, but it's important to know. It's just play with them. Just go play with pandas, see what it does, make mistakes, and learn. So yeah, this is just a high level expansion. So these slides just offer details on the libraries, but I gave the exercise intentionally because I knew you're going to interact with them and at least know how to use some of them. But we're going to do more practicals on them as we go on. So, any question on Python, the libraries, or anything that you've done so far before now I proceed to what you're supposed to cover for today's class? So, we're all good so far. Maybe you don't have a question because you've not understood, or maybe because you've understood everything. So if you've understood everything, okay. If you have not, say something. Hello, guys. I want us to have an interactive session. So, like, any comment, anything will just push me to go on. I don't want to leave anyone behind. Also, so somebody unmute your mic. Just say something if we have understood. So, Mary Ann, you're saying you have not missed the class. I don't understand. But if you missed the previous class, there is a recording. You can catch up. But basically, we were just learning about Python. So make sure you catch up so that you don't get left behind. And also now, I assume we're all good. So we can start today's class on now machine learning overview. So machine learning overview. So you remember we did an introduction, then we said there's AI, then there's machine learning, then there's deep learning. So we said AI is, the big, it's overall, then machine learning is inside AI, then deep learning is inside machine learning. So basically, we are trying to teach machines how to collect data, learn from data, so that you can maybe make predictions, maybe make an analysis depending on what you want, maybe even make anything we can do with data. We have to feed the machine the data. So basically, machine learning is just about making, how do they learn? How do we teach those machines to do that? When I say machine, it's just a computer. Don't think of it as machine. So upon completion of this course, we'll understand learning algorithm definition and machine learning process, related concepts such as hyperparameters, gradient descent, and cross validation, and common machine learning algorithms. So if the words feel complex, don't worry, because at the end of the course we will have understood everything. So we're starting with machine learning algorithms. So machine learning is often combined with deep learning methods to study and observe AI algorithms. So I'm just going to use this example to explain the concept. So a computer program is said to learn from an experience with respect to some task, and the performance is measured. So how do we do it? So we are giving the computer a task, then it will learn from the experience. Then we're going to measure its performance. So if it's not performing well, we're going to do something. We're going to do more until it learns and until that task is until it performs well. I don't know if you're synchronized here. Let me see if the notes can simplify. I don't want to explain a lot about deep learning right now. But basically, machine learning simplified, it's like we are giving computer information, then it learns, then we're going to test if it is learning well. And then if it's not learning well, there are some things we can do about it. Maybe we give it more information, or maybe we increase the learning rate, we just make it learn. So as it learns, we're going to check if it's actually learning well. We have to evaluate, because that's how we manage to get an output. We just give the computer information, then we evaluate. Then if the performance is not great, maybe give more information, or maybe refine, maybe fine tune until it learns from the information that we are giving it. So let me just simply from the data. So I remember when we were doing our first exercise, there was question on rule-based system, that I said it's like the traditional programming, then the AI system. Then we say that we're going to encounter it. So basically, that is for the next slides. But this is just another explanation of how the machine learns. So we're going to give it data, then it will learn. When it learns, we can now give it new problem. Based on the experience, it's going to give us an output. Think of it this way. Um, this is like the expansion is like more of on the deep learning end, but let's say for your life, let's say personally, when you don't when you experience something that you've never experienced before, your mind does not know how to handle it. It's going to get confused. But then after some time, when you experience the same thing that you've had experienced before, it is familiar, and now you know how to handle it. So basically that's how a machine does. We are going to give it data, then it learns. So when we give it a new experience, it's going to pull information from the data, then it's going to give us an output. So I hope that one has sorted the expansion of machine learning part. Yeah, so this is the comparison between the traditional or the rule-based system and now the AI or machine learning algorithms. So the rule-based system, the normal programming, how we make programs, we give it, we call it the rule-based system. We give it a condition. If the condition is true, then do this. If the condition is false, then do this. So it's like we already defined what it will do in all the conditions. If you encounter this, do this. If you find this, do this. We usually have those long flowchart explaining how the code will work. The first, the input, then it processes, then if it's true, proceed to this, maybe execute, give the output. If it's false, proceed to this part, do this, then give the output. But now, the machine learning, we're not going to give it conditions, we're going to give it data. So we give it training data, then it learns. So the learning part is where the machine learning algorithms come in, which we're going to cover in a few. Then when it learns, we have created a model, a machine learning model. Now we're going to give it new data. Based on what the machine had learned before, it's going to give us a prediction or an output. So models are trained on samples. Decision-making rules are complex or difficult to describe. We have not told the computer, this is how you learn the data. We've just told it, just learn the data, memorize it, memorize it. So when we give you a problem, when we tell you predict this, give us this, it's going to give us the output. Then machines automatically learn rules. So this is the difference. They both coexist because there are some systems that excel on the rule-based method, and then now we have the AI systems that excel on the data systems. So we can't say like one is obsolete. No, they both coexist. That's why it's important that you also learn the normal programming, then now how we integrate it with AI and etc. So when do we use machine learning? I know every day we are interacting with AI. Nowadays we have like everything, literally everything online. It's AI. So machine learning provides solutions to complex problems, or those involving large amount of data whose distribution function cannot be determined. So for example, consider the following scenarios. Rules are complex or difficult to describe. For example, speech recognition. So a machine is able to learn speech from different data, and it's able to master. Basically, let me just give an example of how much data like a model can take in that I don't even know if we human beings can process. When you're coming up with these big large language models like ChatGPT, we give it like terabytes and terabytes and terabytes of data. A lot of data. We just collect data from the web, collect data from libraries, online libraries, collect data from maybe institutions, any kind of data. Then you're giving it to a machine. So machine is able to learn such complex, it's able to do such complex task. Then now when you come and ask it a question, it's able to give you an answer based on the data that it has already learned. So it's able to do complex tasks that even us human beings are not able to do. You're not able to go through everything in Instagram and try to analyze and try to come up with a pattern and everything. It's just complicated for us, but a machine can do that. So another scenario is when maybe where the tasks change over time. For example, part of speech tagging, in which new words or word meanings can be generated at any time. And also, another part is where data distribution changes over time and programs need to adapt to new data constantly. For example, sales, trend, forecast. So these are just, scenarios, but we have like a lot of scenarios where we're able to give machine data, then it learns, then you're able to use that data to get maybe a prediction or an output, depending on what you want from the whole exercise. Yeah, so this is just a comparison of rules and when we need to how we need to improvise. For example, when the complexity of rule is low and the scale of a problem is small, just it falls on the simple question, this box. Then, when the complexity of rules is high and the scale of the problem is small, that's why now we come with the systems that we already have. Then, when the complexity of the rules is low, but the scale of the problem is large, we can have like rule-based algorithms. We create an example of a rule-based algorithm is like a function. Last week we covered something about a function. It's like you can create a function that can simplify your task. I know we didn't get too deep into the functions, but you realize that you can create like complex functions that are able to do like some sort of complex work. So it's like a rule-based algorithm. Now, when the complexity of the rules is too high and the scale of the problem is so large, that's where machine learning comes in. So it's like it's solving this other dimension. So as you can see, each has a part to play depending on the type of problem that you are trying to solve. This is another example of we give it data, then it learns, then we give it new information, then we test. So one thing I want all of us to understand is like when it comes to computers, even when it comes to programming, how we have made computers learn and even be able to interpret what you want to tell them, etc. It all narrows down to, I don't want to say math, but there's always math behind everything. So there's always like a math behind how a computer operates. So don't get too caught up in the formulas. You just need to understand what they do. I think that's the most important bit. So we have several machine learning um, tasks. The most common ones, common machine learning tasks. The first one is classification. So we are trying to classify. Let's say when you're doing a sentiment analysis, you want to see if if these tweets are positive or negative. You're classifying positive or negative. Let's say you're working, or maybe let's say you've improvised a solution for a customer feedback. So you can run an algorithm that will classify if this feedback is positive or negative. So just basically classification. This one falls in this category. This other one falls in this other category. The other task is regression. Regression is we're trying to predict the output. We had these sales last year, a time like this. What will be our sales this year? These things are important in helping maybe in budgeting. It's like you're trying to predict the outcome of based on the data that you have, based on a lot of factors, because these algorithms are able to pick even some factors that we even can't pick from the data. Then there's another one that's called clustering. Clustering basically is grouping. So we have some algorithm that will just group data. They're able to identify similar patterns in the data and then they put them in different clusters. Yeah, so these are the main tasks that can be solved by machine learning. Classification and regression are the major types of prediction. The output of classification is a discrete class because it's either it belongs to this class or this other class, or depending on how many classes you have, but it's discrete, this or this. But then the output of regression is continuous. Can be a value, can be a number, depending on the scenario, but it's usually a continuous value. So with time, we're going to learn what are some of the algorithms that are going to give us this these solutions: classification, regression. What is the data that they take in? What are some of the important things that they consider? How do we do it? And so don't worry about the terms if they feel difficult, because I'm hoping that you're going to understand as we go on. So before I go to the next subtitle, any question? Or comments?
I have a question.
Uh-huh.
Can you repeat? It's not even a question. Can you repeat on classification?
Okay. So the classification, even from the name classification, we are trying to run an algorithm, maybe on a set of data. Then we want it to classify. Let's say I've given an example of, let's say you're working in a customer feedback area, then you're trying to see which comments are positive and which ones are negative. But then let's say you're working in a very, very big organization. So you're not able to go through each and every comment and read this one is good, this one is bad. No, it's a lot of task. So you just run an algorithm in that data, then the algorithm is able to classify this one is a negative comment, this one is a positive comment. So you can maybe do an analysis. How many positive comments have I gotten compared to negative comments? What does this mean for? So you're not, let's say you're not able to go through all those comments by yourself. But now you can now use this machine learning algorithm to do the task for you, to do the classification task. So basically, the algorithms are the ones that are doing the task. We're not the one who is doing these tasks. We have other scenarios for classification. I don't know if, though this one falls in, let me give a simple example. Even a simple example, if you're trying to tell a computer, I want you to differentiate between um, which fruit is ripe, which one is not ripe. It's going to put it in categories. This one is ripe, this one is not ripe. So when it comes to classification, there are categories. There are categories to that. The output will be either it falls in this class one or class two or class three, depending on how many classes that you have. I don't know if you've understood, or should I give another example of classification task?
I've understood.
Okay. So we are not the one doing this task. We are trying to give computer a lot of data. We're trying to tell an algorithm, run through all the Twitter posts that have been posted in a day today. How many Twitter posts have been posted today? A lot. Then we're trying to identify what percentage falls in this category. Are these good tweets? Are these bad tweets? Are these, should we delete these tweets? Depending on, we are trying to make a computer do that work for us. So we're not able to go through all those posts and evaluate this one is good, this one is valid, this one is not. No, but then you can make a computer do it, given, you know, depending on what you want to do it. So that's basically classification. So any other question?
Yes, I have a question.
Yes.
I'm trying to understand the difference between classification and clustering. I
Mm-hmm.
understand in classification, is it that it is explicitly two categories that you are trying to differentiate the data, like if you're male or female? And in clustering, we have multiple classes that you're trying to classify the data. I don't really see the difference that much. If you could expound on it further.
Okay, so classification, it's not really like two classes. You can classify into any number of classes depending on the how many classes that you have. But now, okay, clustering is where now you are giving a computer, it's called unstructured data. Let me just give a small I know you're going to meet it, but let me just give a small explanation here. We usually have structured, let me just call it labeled, don't know if that's, or structured, they're kind of interconnected. Then we have unstructured data. So for the labeled or structured data, it has a definite outcome. Say that I've already trained a computer and told it, this one is good, this one is bad. Okay, let's say I'm classifying birds. Let's say I have 10 classes of birds. So I've already given the computer, this is hummingbird, this is morning, I don't know many birds, this is an ostrich, this is this is, so we have already trained a computer giving it solutions. Now when we give it a bird, it's going to classify into the classes that we've already told it to classify. But now clustering comes in when we have unstructured data. Unstructured data, it's not organized. It's like you just have like large data. You don't even know what is in that data. Then you're giving it to a machine. Then you're trying to say, look if this data can make sense. So it's usually when it comes to clustering, you don't even know what the computer will come up with because you've not like told it this is the outcome that I expect. You're telling it learn the data, and then based on what you've learned from the data, now do something with it. Most of these algorithm, they just go in, they learn the data, then they group some stuff into classes because maybe they have noticed like a similar pattern. So maybe when now humans, when we come in and start trying to see why is this clustered here and here and here, we're going to see that this one is common, this other group is common, the other group is common, etc. So clustering, we don't tell the computer this is the output that I'm expecting. I'm not telling the computer I'm expecting you to say this is positive tweet, this is negative. No, I'm just telling it, just learn from the tweets. Learn as much as you can. Classify them. Understood?
Yes.
Yeah, so that's the difference. I'll delete this part. Any other question? Oh, also, if you're writing a question in the comment, I'm not able to access the comment session at the moment. So you can just unmute your mic and ask. That will be easier. Okay. So types of machine learning. This is it now. I have semi-explained in the previous slide. So we have types of machine learning. So don't forget, the previous one was the tasks of machine learning. What are some of the tasks that we can do with machine learning? Now, these are the types of machine learning. We have supervised learning. This is where the program takes a known set of samples and trains on optimal mode to generate predictions. Then the trained model maps all inputs to outputs and performs simple judgment on the output. Okay, so this is what I was telling you. It's like you're giving it labeled data. You're telling it, learn, this is it, learn from this data. This is number one, this is number two, this is number three, etc. Now, when you give it a random number, it's able to classify or do a regression depending on the task. But it's already labeled data. It's already defined. This is the output for this. And supervised learning is now those clustering algorithms come. It is building a model based on unlabeled input data. So, for example, a clustering model groups objects based on similarities, and a supervised learning algorithm model the highly similar samples, calculate the similarity between new and existing samples, and classify new samples by similarities. So we are giving this. It's okay. People know you guys know big data. It's like we're giving this model just data. Take this data. I don't know. We're trying to make sense of the data, but we can't go through it. We are human beings. That's too much work. So the computer will just learn from the data, then it's going to cluster, it's going to categorize, it's going to draw patterns from the data. So that's unsupervised learning. Then we have semi-supervised learning, where a program trains a model through a combination of small amount of labeled data and large amount of unlabeled data. So it's like semi-supervised. We give it a small percentage. It's like we are training it with the input-output mapping for short time. Now we give it a large amount of unlabeled data. It's also a type of semi-supervised learning. And then we have reinforcement learning. Reinforcement learning is where the learning system learn behavior from the environment to maximize the value of reward. So, and a good example of reinforcement learning, it's the technology that is used in the autonomous vehicles. Those, autonomous vehicles, games, etc. It's like when it's like you're telling a computer, you're teaching a computer, it's like I kind of call it a reward system mechanism. So when it performs well, you reinforce that. Then if it does not perform well, then you won't give it a reward. So it's supposed to, change how it has performed and perform well. So basically, if you would like to measure into things like autonomous vehicle, games, anything autonomous machines, you're going to deal with reinforcement learning. So you're telling this vehicle, learn from your environment. So if it drives this way, then it hits a tree. It gets, maybe it can even get a punishment. So it will going to learn, when I go in this direction, I might hit an object. So I'm not supposed to do that. So it's like some sort of reinforcement. I don't know if I've given a good example for the reinforcement one, but it's like you're trying to tell the computer, learn from the environment. So if you perform well, we tell you well done. So the computer will be, okay, I performed well. If you perform bad, we tell you, no, don't do that again. then it will learn, okay, that is bad, I'm not supposed to do it. So with time, even for robots, I think big part of the robots are using reinforcement learning. It's like this action is good, this one is not good. So over time, it gets to learn which are the good actions that it's supposed to take, the bad actions that it's supposed to remove from its system, and so on. So machine learning evolution is producing new machine learning types. For example, self-supervised learning. This also part that is combined also with the reinforcement learning nowadays, contrastive learning, generative learning. So because there's a lot of research on AI nowadays, we're also coming up with new, it's an evolving field. So we're coming up with new things, and but so far the ones that we're going to interact most with, this one, these ones, yeah. But then you can come across other types of learning, which is still okay because it's an evolving field. Any question? So supervised learning, as you have explained, we have the data. So when we have the data, let me just do some small illustration here. Okay. Allow me to create a new slide. We have data. Then we have output. Let me give this an example. I have orange, then I'm telling the computer this one is an orange. Maybe I have a mango. Okay, I have a mango, then I'm telling the computer this one is a mango. So I'm going to give it the label data. The label data is literally, I'm giving this computer this data that has an output. So it's going to learn from that data. But when I say it's not really simple, you can give it as many properties as possible. It's a machine. It's going to learn. So you can give it as many. Let me give you a weird example. Let's say you're in real estate and you want to do like predictions of houses based on their features or their characteristics. Features is a very important term. So let's say it can have like 2 bedroom, the white tiles, I don't know which color of the wall, the kitchen size, the bathroom size, maybe it has a bathtub, the balcony, backyard, blah, blah, blah. You give it all the features of that house, then you give it the price. This is $1 million. Then you give it different types of houses that have different features and their prices. So this price part is the output that probably want to predict for new houses. Let's say the price is the output. What have I done? Okay. So the price is the output. So we're giving it like a lot of features. Learn from this. When the house is like a story building, this and this, it has these properties, it has a black roof, all these different properties. Then this is the price. It's a mansion, it has these properties, this and this and this is the price. It's a bungalow, it has this and this is the price. So next time it has learned from that data. Now we want to use it for prediction. So if somebody now calls you and tells you, I want a house that has this and this and this, what will be the price range? So what you're just going to feed those features to the machine, because it has already learned from the data that you've given it. It's able to predict the price based on now the new features that we're giving it. So features can be many, can be few, but most of algorithm, they excel on a lot of data. So it's not bad because they're able to create the relationship between the input and the output. Yeah. So this is the example of a supervised learning. So you give it features, feature one, feature two, feature three. Then you tell it to learn from it. Then now you come and ask it a question. Then you tell it to predict. For example, we are trying to predict weather here. So we say the weather is sunny, temperature is high, the speed is high. Is it suitable for exercise? Yes. But we are giving it, we are making it learn. If the weather is rainy, the temperature is low, the wind speed is this and this, is it suitable for exercise? We tell it a no, etc. Now, one day you just wake up, then you're like, so today is sunny, this and this. I want to know if today is a suitable day for me to go for run. You're just going to give it to feed that information to the computer. Then it's going to give you a prediction because it has already learned from all those features. I hope you're together. So that's how supervised learning works. So remember, we have regression tasks and we have classification tasks. So regression reflects the features of sample attributes in a data set. So regression basically assumes that these features are connected to the output. It creates a relationship. So it's able to identify if this property and this and this and this, then this is the possible outcome. For example, how much money can I make from stocks next week? So you've been giving your machine learning model a lot of data on stocks. So if this is the condition, if the trade market is like this and this and this, if the all those information, this is the money that I'm making. So now when you try to ask how much money will I get from stocks based on the data that you've already given it, it's able to predict how much you're going to get. For another thing is what temperature will be on Tuesday. So these are some of the algorithms that are used even in our weather apps. When you wake up, then you check your weather app. Then it tells you today is going to rain. But it's clearly sunny. Then in the afternoon it rains. Then you're like, oh, my weather app was correct. Because you've been feeding it, it has been fed with a lot of data that it's able to predict how today will be based on the data that it has already been fed. Another example, I had another example. Okay, I've forgotten. We have far too many examples because if you're realizing we interact with these algorithms on every day. Oh, the other example, the apps that we usually, as ladies, we usually use for our periods. You give it your data. This is my height, this is my weight, these are my days, etc. So based on that data, it's able to correctly, the more you give it data, the more it learns about you, the more it is able to correctly predict your days. So this basically that's an example of supervised learning. Another category, classification. It's the same thing, giving it data. You're telling it this data belongs to this class, this A belongs to this class, B belongs to this class. Now, when you're asking it if which class, now you're using it to maybe predict which class this belongs to, it's able to do it. For an example is the email spam. I don't remember the exact year, but there's a time when email spam was a real problem. And then they were able to deal with spam email, though not all of them, because sometimes you can find a genuine email. You're invited for an interview, then it went to spam, so it happens. But then it's able to classify emails as spam. So when they implemented this, spam email became less of a problem because even when the email clicks your inbox, the algorithm is able to see, no, this email is from a betting site. This email is from this and this. This email, it's not genuine. Then automatically it dumps it in the spam because we've already taught this how spam emails look like. Yeah, so that's another example of supervised learning. So I want you to know that all this learning can perform the same task. We have the tasks: classification, regression, and clustering. So supervised learning, we have regression. Okay, we said classification and regression are the most common tasks. So for supervised learning, we can have regression tasks as well as classification tasks, depending on what you want to do with your algorithm. And supervised learning, this is where now the clustering comes in. We are just giving it data. Giving it data, as I have explained. So we call them features. Then now, because of we don't expect, we don't have a defined expect or a defined outcome, we're going to get clusters. It's going to cluster out the data. Then from there, we're able to check, why is this cluster here? Sometimes you realize, wow, they have similarities. It just, let's say you give it like a large customer data, you're this multinational company, then you just give it large customer data, then it just clusters. Then when you dive deep into the clusters, you realize these customers have similarities. Maybe they come from the same background, or maybe they're in the same age group, maybe they're the same gender, etc. You're able to learn, you're able to derive insights from those clusters depending on the data. I think I have an example here. For example, recommending movies for users, recommender systems. It depends. As I've said, these things are everywhere. You have your Netflix account, just to watch one teenage series. All of them are going to come to your suggestions because the algorithm is able to identify, you've watched this is similar to this is similar to this and this and this. Then it gives you some suggestions. Sorry for that. Yeah, so any questions so far?
I have a question.
Yeah.
Is it only in supervised learning regression
Mm-hmm.
that prediction takes place?
Come up again.
Is it only in supervised learning regression
Mm-hmm.
that prediction takes place?
Yeah, most of the time, because when we are doing a prediction, okay, we are going to learn, these are machine learning algorithm. We're going to learn about deep learning. But so now prediction for deep learning is different. For example, how ChatGPT generates data or the text, it's based on also some sort of prediction. This is connected to this. This is the conversion that we are having, which means this word will connect to this and connect to this and connect and eventually form a sentence, then eventually form a paragraph. But now when it comes now to machine learning, so that is deep learning. But now when it comes to machine learning, mostly regression, yes, is used for prediction, especially when you are trying to get a continuous output, like a number, you know, a defined, a continuous, a number, mostly continuous, mostly a number. Yeah.
Okay, thank you.
You're welcome. So semi-supervised learning, the same. We're giving it a small amount of labeled data. Then we're giving it large amounts of unlabeled data. Then we're telling it, learn from that data. Yeah, basically it's what I've explained. These are just more some diagrams to assist you in understanding, to visualize the process. Then reinforcement learning, the way I said, it learns from the environment. Take action and adjust the action based on the system rewards. So the model, we have the model. So when you talk about model, in this case, it's now the machine learning model takes an action. Depending on the output of that action, the output now from the environment, you can get a reward or maybe a punishment. Then it will learn this is not good. Then take another action. as I've said, how we teach robots, how we teach autonomous vehicles. It learns, it's that system, reward-based system. This is good. So it records, this is good, this is bad, I should not do it. So this is mostly illustrated in games. Mostly when I want to give an example, but I don't want to give a complex one. Mostly in games. And let me just say in games. So when you take this step, let's say we are playing chess. When you take this step, then it's checkmate. Then the machine will learn, oh God, so that is a bad step. So when we're in this position, I'm not supposed to go this direction. So it has taken that into consideration. Then when it takes another step, it's a whole process with a lot of data, but now the machine eventually is able to identify this is the right step, after this step this is the next one, this is the next one, and so forth. So eventually you get a full model that has learned from that reward system. Okay, so an example, I've given this example a lot of times. Let's see the robot vacuum. The battery is level 10% and a small area is not cleaned. Should the robot continue cleaning or recharge? Because you want to automate the process. So you have to teach the machine on what are the best actions to take. So eventually the machine learns on the best actions to take. Then with time, with refinement and with time, they get to learn this the best, this not the best. If I'm in 10%, there's a small area, maybe I can finish it up. We're trying to automate our processes because that's the point of AI, that's the point of machines, automating the processes, making our life as simple as possible by making machines do the work that, you know, is complex. We have another part of machine learning process. This is like a life cycle of machine learning. We have data preparation, then we have data cleaning. As I said, when you're feeding data to a machine learning algorithm to create a model, the quality of data determines the output of your model. So it's so important that you do your data cleaning. We have another section that is called feature selection or extraction, depending. And I've said features, these are the properties, these are the aspects of the data that the machine is going to learn from. They're called the features. So some features are kind of irrelevant, others are important to bring out the output. So this is where that stage comes in, feature extraction and selection. Then we do the model training. The model training is where now we feed this data to a machine learning algorithm. Could be a regression algorithm depending on the task that we aim to accomplish. Could be a classification, clustering algorithm, depending on the type of data. Now we already know we have the labeled and unlabeled data. Depending on the type of data and the type of task that we want the machine learning algorithm to do. So when it learns, it becomes a model. So there's a part that is called model evaluation. We are evaluating, has it learned enough from the data? How do we do this evaluation? Let me create another slide here. So evaluation, when we have the data, we are going to divide it into train data and test data. So train data is the data that now the algorithm will use to learn to create the model. And then the test data will be used for evaluation. Most of the time, it's usually like 80% training. Don't even know what these slides are doing. 80% training and 20% for testing. Depending on your data, you can do 70-30, 75-25, depending on the scenario. It's not like a fixed, but the standard is 80-20. So we are going to evaluate it based on our test data. So don't forget, our test data is already, it's also labeled. So we want to see how has this model performed, how has it learned from our training data. Now when we test it, how many predictions are correct? Because now this all data is labeled, the train and the test data. But we want to see, is this has this model learned enough from the training data to be able to predict well? When we see that the model has learned well, we can proceed to deployment. But most of the cases, as an AI ML engineer, you'll find yourself rotating or maybe doing some fine tuning here. It's usually a process because sometimes they learn fast, sometimes they don't get it at first, then you iterate until when you evaluate the data, it has learned well. Now you can deploy the model and integrate it. Can integrate it into existing systems. For example, a recommender system is already integrated into literally every app that you're using nowadays. Spotify, etc. You'll find recommendation based on the things that you like, depending on the environment that is being deployed. But you have to ensure that the model is fine. And we said a very important step is this, data cleaning. If your data is clean, your model will learn well. If your data is not, oh my God, it's a lot of work. You'll start afresh. So we have talked about data, and we say from the knowledge that we know, data is information. Basically, that's like the simplest definition of data. It's information. So I've said training set and test set. So a data set, what is a data set? A data set is a collection of data used in machine learning task, where each piece of data is called a sample. Items or attributes that reflect the presentation or nature of a sample. Oh God, this is too much English. They are called features. So features describe the data. But I think from the previous slides, I already said these are the features. Like they are giving the output an attribute. The house has two bedroom. You are giving it various features. So the machine is able to learn from the features and create a relationship between the features and the output. And now it's able to, do those tasks that we intend for it to do. So we have a training set that is used for training. This is where now the data that model learns from. Then we have the test set. I think I had explained a little bit from the previous slide. And now, yeah, the test set is usually a small percentage, as you can see from here. So we have these are the features: area, location, orientation. Then now the label, the output, the intent. We eventually want our model to be able to predict the price of the house. So this is the label. So if there is 100, the location is 8, the orientation is south, then the house will be this amount. So we train it on the data, then we test it. If it predicts well, we know it's going to perform well outside. Now we know it's going to perform well. Now we give it new data that has no output. Yeah. Any question so far? Any comments? Are we together?
Yes.
Yes.
Okay. So as we said, important of data processing. Now this sounds like a new concept, but in essence it's not a new concept. It's these three parts, this and this, called data processing. Because we're not yet given that data to the model. We're not training it. We're trying to process that data. We're trying to make it fit for the model. So with time, we are going to learn different ways in which we're going to process the data, depending on the type of data. And let me tell you guys, out here, hey, there's all types of data, but now there's a way that a machine will learn effectively. So we have to also tune that data into a way that the machine is able to learn from the data and actually give us a good output. So we have data cleaning or cleansing. Uh, this is where we fill in the missing value. We we eliminate the duplicates, we eliminate the noise, we eliminate outliers. If I'm trying to sell a house in a specific estate, then in my data there's just one house that is a bed sitter, it's going to alter my how my machine is going to learn. So it does not fall in that category of the type of data that I want my machine to learn. So I'm supposed to remove it. Yeah, so that's data cleaning. Mm, dimension reduction. This one, I think it falls on feature selection. Simplifies data attributes to avoid the curse of dimensionality. What is the curse of dimensionality? Even from guesswork. Why are we reducing dimension? But I think this is a complicated term at this stage. I'll just attribute this one to feature selection. Yeah, I'm hoping that you're going to encounter it in upcoming. Okay. Yeah. Then there's data standardization. We are standardizing the data to reduce the noise, to improve the model accuracy. As we've said, the type of data that we're giving the model determines the quality of our model. So we need to standardize the data. Yeah, I think that's okay. Yeah. A data scientist spends a lot of time doing data cleaning. As I insist, it's very important. So we have, okay, this is just a statistic according to, this is for 2016. So maybe right now you can find the statistic is different, but I think I have overemphasis, but it is important to know that data cleaning is very important because it determines the quality of the model. If you do good data cleaning, if your data is high quality, you don't even need to retrain the model. But if your data is bad quality, just you can even start again from scratch, and that is usually the worst case scenario. So yeah, because when it comes to training, you're not the one doing the work. You're just going to feed the data to an algorithm. Then now the machine will learn from the data. Then it's going to output, predict, etc. So you get why data cleaning is important. It's like that part where you as a human being come in to determine the type of data that you're giving the machine. Yeah. So basically, this is a more expansion on data cleaning. We have said handling duplicates, handling abnormalities, merging data from different sources, data consolidation, filtering, depending on the data that you have and the task that you want the machine learning algorithm, okay, the model to do, and the type of learning that you want it to do. So these are all relative depending on the scenario. So we have some example of dirty data. For example, data can be incomplete. You can find null values. So you have like large data, but there are some spaces that are null. So we don't want to guess. We don't want to guess this value. So it depends. Sometimes we have ways of handling null values. We call them missing values, etc. But then it's important that data is complete when you are feeding it to the model. So all this depend on the scenario also, as I've said. Different methods apply for different types of data. When we want to teach a model to do a different type of task, etc. So we have noise. Noise is abnormal points, outliers. So this one is an example of a missing value. We have another example of invalid value. So let's say we're supposed to fill in gender, either F or M, then there's A. Clearly, it's an invalid value. Then we have inconsistency. So for this, I think this part is well. As you can see, the date is given in the date, month, and the year. But now this one is the year, the month, and the date. So it's already inconsistent. It's not aligning with the rest of the type of data. So that's another part we need to clean. We have duplicates as seen here. We have misspellings, etc. So sometimes we have columns that are dependent on each other. I think this one is clearly, for example, is teacher. If you don't have a teacher, how can you have 5 students? That's not correct. So that's where the human aspect comes in. We are able to check and see, no, this one does not make sense. No, this one is inconsistent. This one, we want the model to learn with the most accurate data as possible. So this is just an example of a dirty data. I know it's all dirty. It's just one picture that shows all types of dirty data, but they come in different forms. Not all your data will look like this. So look out for those different forms of dirty data, etc., depending on the data that you're handling. We have now converting data. I think now this is where we come, this part. For example, dimension reduction, etc. Data conversion. Preprocessed data needs to be converted into a representation suitable for machine learning models. So I'll give us a small example of computers. So traditionally, computers, okay, we all know that computers learn in binary, zeros and ones. But now, because we have these high level programming languages, we're able to come up with these UIs, user interfaces, that now I'm able to access Microsoft Word, PowerPoint, without actually, coding those zero and ones. That is happening in the background. I'm not the one doing it. So because a computer is a computer, it doesn't learn how we learn. It won't see this date, then automatically assumes this is today's date. We have to convert it into a mode that is suitable for that machine learning algorithm to learn, so that it can create a model. So we have various ways in which data is converted. For example, we have encoding. You're going to meet a term that is called one-hot encoding. It's just a type of encoding. It's where we turn categorical data into numerical data. You don't have to worry about this. You're not the one who's manually doing the encoding. As I've said, Python has a lot of libraries. You're just going to import one-hot encoding, then you feed your data to one-hot encoding, then it does the magic, then now you feed it to the model. So you just need to learn how to use those libraries. You need to learn when to use them. So a machine is not able to read, this is a book, this is a pen. No, but we have to convert that data into a way that a machine is able to record and maybe eventually give us a great output. Another way of data conversion is converting numeric data into categorical data to reduce the values of variable. For example, segmenting age data. So you'll find sometimes you're doing the opposite. You want to group this category into a certain age group, from 0 to 5, from 5 to 10, from 10 to this. You want to put them into different categories. Other type of data conversion is embedding words into text to convert them into word vectors. This one is used by these big, large language models like the GPTs. GPT is basically like it's called transformer, but don't worry so much. I think we're going to cover our last week's, we're going to cover more about NLPs. Yeah. We also have another technology that is called BAT. So we have to take these words, convert them into a form that is called word vectors. Then now that's how the machine understands. That's the language that the machine understands. Another form is we have image. We have the normal image. Then now we able to put it into, we have several things that we do to an image to enable a machine to be able to detect or even to be able to learn from that image. So, for example, it could be space conversion, grayscale conversion, geometric, etc. This is for computer vision. And this, the first point is for natural language processing. And now we have another part that is called feature engineering. Feature engineering is where we are trying to pick the important features. Let me just use that example for houses. So I've given this feature, the house, the height, the walls, color, the flow, this and this, where it is located, electricity, etc, etc. And then maybe there's just another irrelevant column that does not add to the features. Or it's not important in predicting the price of the houses. So we can drop that column. We can drop it. And also, like, is the house washed or not? Like, I don't think it is going to contribute to the price of that house because it's not relevant. So yeah, so those are some of it's called feature engineering. It comes in different form. For example, feature selection and feature augmentation. Okay, so I'm still going to encourage you guys, if you're learning like a lot of new words for the first time, it happens. Don't feel overwhelmed, just relax. The next time you're going through this, it won't feel new to you and you'll understand it even better. So yeah, I still have to keep that balance for you guys to understand what we are doing here. Yeah, so when it comes to feature engineering, we also sometimes you have some libraries that can also do this for us, that are able to identify the important features that are connected to the output and irrelevant features. So yeah, it's important. So how we process the data to give it to a machine, it's a lot of processes. There's the cleaning, there's now the conversion part, and let's see what is here. Yeah, I think the conversion, because I think feature selection it is falling in this category, feature engineering. So before I proceed, any question or any comment or any concern? So we talked about feature selection. A dataset may have features, some of which may be unnecessary or irrelevant, as I've said. It's not contributing to the output. These are just an irrelevant column. It's not giving any information. So we can select the most important features and leave out the rest. We have various ways in which we can do the feature selection. I'm not going to go in depth with them. The first method is filtering. The other method is called wrapping, and the other method is called embedding. So all these are relative, as I've said, depending on the scenario. Sometimes you even have less features, so you don't even need to do the feature selection. Sometimes you have a lot of features. You can have like thousands and thousands of features. So you need to do feature selection depending on the scenario. So this is the overall process now of building an AI model. So we have been through it, but it's good that we overemphasize so that it sticks with us. So where do we start? Step one. We've already done the cleaning, guys. We've already done the cleaning, the conversion, uh, those parts. No, we split the data into training, validation, and test. So I think I should explain a little bit about the validation data set here. I said the training set. Um, then I talked about the test set, because we are training the data, telling it this is the input, this is the output, this, learn. Then now we come to test it. Has it learned? You know, okay. So between here, sometimes people may choose to do validation before testing. What is the ratio for this? I think I'll give it 70%. Then I can give them 15% of the data set. So the training is where we're going to do, we are training the data, we're training the model, train, learn. Then in our case now, validation will act as the test set. We're going to give this model the validation data and to see how it is performing, because remember, this data is labeled, it has the input and output. So we already, it has a non-input and a non-output. So it's like we are trying to see if the model has learned, so we take it through validation. Now test will act as the new data, now the new data that the model has never seen, does not have a reference. And because we, the people training the model, has the reference, we're able to see how the model is likely to perform in an unseen data. So most people prefer this method, training, validation, and test. Some people just prefer just training and testing and, deploying the model. Yeah. So that's where the validation comes in. So we split the data into training, validation, and test. We train the model. We use the data that is processed by data cleaning and feature engineering to train the model. We validate the model. We are checking, has this model learned? Evaluating, validating. And then we test. We are testing it on unseen or on new data that it has never seen, and see how it is performing. It has already gotten familiar with the training data validation. Now, if we give it completely new data, is it able to give us the correct output? If that's okay, we deploy the model to production, push to production. Then we can continuously tune the model. Some companies have data coming in every day, so they prefer to retrain their models after some months, add new data, etc. Because we also understand that it's a dynamic economy. Maybe today, when you're starting the year, you have 100 branches across the country. Then now you've expanded. There's this new data. There's this new things coming up. So maintaining that model, adding data periodically, depending on the situation also. So this is the overall process of building an AI model. Yeah, so these are just examples of the learning phase, the prediction phase. Yeah. Any question or any comment or any concern? So it's valid to assume that you're good. Then come to ask, what is a good model? So a good model, it's able to accurately predict, and the predicted results are easy to explain, and then it can predict as fast as possible. Yeah, so these are some factors. These are like quality QA factors that you're considering. You don't want to prompt ChatGPT, and by the time it gives you an output, you're already tired. You've already gone to Google and researched and found your answer, and now it's telling you, "Oh, finally, I've come up with my answer." No, you want fast prediction. You want a model that's able to predict as fast as possible, but also predict accurately. and also give you an easy to explain answer. So this is like properties of a good model. So these are some of the things that you're supposed to consider as an AI ML engineer. Like, is my model, how is the generalization? How is its output? How is the prediction speed? These are creating a balance between this will make the model like in the category of a good model. So we have model effectiveness, generalization capability. We want the model to learn, but also to be able to accommodate new data, new unseen data that we're not even ourselves, we've not even seen it. Like, the model will be able to use new data but still give us a good output. That is called generalization. So machine learning aims to ensure models perform well on new samples, not just those used for training. Generalization capability, also called robustness, is the extent to which a learned model can be applied to new samples. We want our model to be able to cope well with new data. We won't always be training the model, so we want it to be able to cope. We have another term that is called error. Error is the difference between the prediction of the learned model on a sample and the actual. So when you're training the data, I'll just use the training and testing scenario. I'll ignore validation for now. You've trained the data, and then now you're giving it the test data. Remember, I said the test data has an output. We already know the output for the test data, but now we are giving it the features without the output to see if it is able to predict well, if it has learned from the training data. Then we compare the model's prediction with the actual prediction. Then we measure the error. So when we are starting, the first part of the slide, we said we give it an experience, we give it a task, then we evaluate. Then, so this part of checking if the model has learned is called the error. So the error is now the difference between the actual prediction and what the model has predicted on the test set. So if the model is able to predict well, so well that it's almost predicting the same as now our test set, now we can see the model has learned well. But we have some factors that we also need to consider. We have a term that is called overfitting and underfitting. Remember that we interacted with these terms when we were doing the first exercise. So overfitting, it's when, like, I'll start with overfitting because underfitting is basically opposite. The model is training so well that it performs so well, but now it is not able to generalize. When you give it new unseen data, it won't be able to give correct predictions because it's like it has crammed that data. These are powerful algorithms, so it can cram that data as it is. So when you give it a new thing, it just performs so poorly. That's called overfitting. Underfitting is where the model does not learn well, so it's not able to predict well. So that's like a simplification for underfitting. So you're going to interact with these terms because when you're training a model, these are some factors that to consider. Is it overfitting? Is it underfitting? Is it robust? Depending, like, as an AI ML engine, these are the factors that to consider when you're training a model. So you're going to interact with them over and over again. And of course, we have methods to ensure that our model does not overfit, our model does not underfit, our model has a small error. We are trying to reduce the error. We don't want it to predict so far from the actual prediction or from the expected output. So we have some methods of reducing the error and also ensuring our model has the generalization capability. Yeah, so underfitting, good fitting, overfitting. This is just more explanation for the previous slide. So the causes of overfitting, we have two terms, bias and variance. The variance, it's how far has the model deviated from the actual predicted or the expected output. Basically the variance. And then the bias is the difference between the average of the predicted values and the actual value. So basically, when you are measuring, when you are evaluating a model, allow me to come to this slide. Model evaluation. So we have trained the model, then we have tested the model. How do we evaluate? Like, remember, sometimes we're giving it too much data, so it's not humanly possible for us to take this output and then start analyzing. We have to evaluate if it's performing well. So we have several ways in which we evaluate, and basically evaluation is seeing how big the error is. How far is the model? How far is it from the actual prediction? Or how close is it? So if the error is big, it means now the evaluation, like if the error, it's an error. So if it's big, then the model is iko inje, it's outside. Then if it's small, then the model has, well, it's well trained. So this has the model evaluation part. Let me come here. So this variance and bias, they are directly connected to the error. So you need to maintain a balance between the variance and the bias for us to get a good model. The good model as we have described in the previous slide. So when we have a low bias and a low variance, we have a good model. We can have low bias and a high variance, still not a good model, not a good model. So the ideal one is having a low bias and a low variance. So an ideal model can accurately capture the rules in the training data and can generalize on new data. However, it is impossible for a model to complete both tasks at the same time. But it's a matter of balance. Like, you're trying to balance, you know. So the more we learn, the more we'll understand how. And all right, now you're asking yourself the questions like how. We're going to learn that as we learn how do we train the model? How do we evaluate? If the error is too big, how do we reduce it? How do I ensure that my model is deployable to real world and actually applicable, because it's able to generalize to new data. So it's a matter of balance. Yeah. So errors, as we said, the point is to reduce that error as much as possible, but also to ensure that the model is not overfitting. It's not cramming the data, but no, it's not underfitting, and then it's able to generalize. So the more complex a model is, the smaller its training error. But now the test error will increase. So we are trying to, as the model complex increases, the test error decreases before increasing again. This is the point that we're looking at. I don't know if I'm able to draw something. No, that's not the point. Okay, this part. So when you're talking about complex model, some people like to just train the model, like use the most complex methods to train the model. So the model will learn and learn and learn and learn. Now it starts overlearning. So now when it starts overlearning, it starts overfitting. So the red curve shows overfitting. So just before the curve starts rising, that's the where we're supposed to stop the training of the model. I feel like I have introduced like too many new terms. So like any question or any concern? So if you have no question, allow me to proceed. So when you're evaluating, we have several ways of measuring the error. Don't forget, we have the error. We want to reduce the error, but make sure the model is not underfitting or overfitting and is able to generalize to new data. That's the point. So the first method of evaluation is called mean absolute error. It's where we're taking the mean absolute error of the performance. So this is for regression. Remember that regression is a continuous value. So we're able to do a mean because it's a continuous value. Also, as I've said, don't get overwhelmed by the formulas. Just know what they do. That's what is going to help you. So the closer the value is to zero, the better the model, in short. Another method of evaluation is called mean squared error. Mm, we are taking the error, it's the literally the way it's mean squared error. Then we have another one under this that is called root mean squared error. And then another evaluation for also regression is called R2 score. Actually called R squared, but it's called R2 score. Yeah. So don't get stuck on the formulas because all these things are already in like libraries. You just from this and this, I think it's from scikit-learn, this and this, import mean absolute error, then you pass your model via it, then you're able to see how is it performing. But then it's also important to understand how they work. When I'm mentioning, when do I use mean squared error, when do I use mean absolute error, when do I use R2 squared, etc. So it's also important, but don't get too hung on the formulas. That is for regression. For classification, because classification is, as you said, it's a discrete output. It's either class A or class B or class C, depending. We have, this is called a confusion matrix. We're able to test various aspects. For example, how accurate is the model in classifying? How is it placing? Is it classifying true classes well? Is it classifying the wrong classes correctly? If a yes or no, is yes where it's supposed to be, is no where it's supposed to be, etc. This is called a confusion matrix. I'll urge you to just go through this slide. But then this is the performance evaluation. We have the accuracy. Then we have another aspect called recall. Then we have another aspect that's called precision. So basically, these other categories will fall between those: accuracy, recall, and precision. How accurate is the model? Sometimes, let me just give a small explanation why we have all this, why are we measuring all these factors. Sometimes you can find imbalanced classes. So when you find imbalanced classes, one class has more data than another. It's usually good to use a different method, maybe sensitivity, the recall, or the precision. It is all depends on the data that you have. So please go through this and try to see which are the scenarios where I need accuracy, which are the scenario that I need recall, which are the scenario that I need to mix accuracy with recall and precision, etc. But at least now you know the evaluation metric for a classification model and evaluation metric for a regression model. Yeah, so this is just some more explanation on how to get how the precision is calculated, how the recall, and how the accuracy. It's good to know this, but Just know that you're not the one who is going to do it. We have like predefined libraries for this, but it's also good to know how it functions. If I'm measuring accuracy, exactly what am I measuring? You know, yeah. So can see it's already 9:46. So allow me to stop there and then to answer your questions if you have any or concerns. So any question or any comment, or I'm taking comment or any feedback from you guys. Sharon Keter,
Yes.
have you understood the class?
Yes, but you kind of lost me up on mwisho, but
Mhm.
yeah.
Maybe
Mhm.
because we have taken like a long time, but just I'll share the notes.
Okay.
And also, if you get stuck, you guys have my email. Just reach out. Okay.
Okay.
Yeah. Anybody else? Karen is saying that the session was good and she has learned a lot. I'm glad that